All right. So just a reminder, next Thursday, don't show up because I won't be here. All right. And the exam for this material will be in Brightspace. Okay. I'm sorry. Yes and no. It's time so I know if a student is going past the time, but it doesn't kick you out. No, I'm just interested in knowing, am I giving you enough time? And if everybody goes past, then I know I'm not giving you enough. And I can make the adjustment for a subsequent class. Okay. So how do we characterize gases? Right. You remember the different phases, right, from early on. So how would you characterize a gas? Nobody has a clue. Right? Well, they have to have low density, right? Low density, right? Because the particles are very far apart. Lots of space occupied by small mass. Right? Density equals mass divided by volume. So you increase the volume to a huge amount with the same amount of mass, the density is going to drop. It's going to be less. Right? So they won't be high density. They're not closely packed. I'm just going down the list of choices. How about no increase in volume when temperature is increased? Right. That runs counter to whose law? Volume, temperature, huh? No, Boyle's pressure volume. Who's next? Remember, we took them in chronological order. Boyle was first, and then I gave you a hint, he was French.
Or
Charles.
Yeah.
Yeah. Charles. Yeah, they like to give first names in the last name position. I don't know why. Must be a French thing. Low density. That's the only one that fits out of this bunch. It's all right. How about number two? How do we define pressure? First of all, is pressure an extensive or an intensive property? In other words, if you have a large amount of something, does that change the pressure? No, it's an intensive property. Usually, not all, but most intensive properties are ratios. Think of it that way. It's a force per unit area. Okay. Now we have other units of measure that seemingly don't include. What are some units of measure for pressure? Right, you're going to have to know those today. Pounds per square inch. Atmosphere. That's a good one. Torr. And torr is also equal to what? Millimeters of mercury. Yeah.
PA.
I'm sorry.
PA. The big thing.
Oh yes. I'm sorry. Pascals. Yeah, right. That's the SI unit. Okay, so pressure has lots of different units that can express pressure. All right, so back to the question. Pressure is what? Defined as a force per unit area. That looks like the best one. All right. How about three? The SI, you've already given me that one. The SI unit of pressure is the Pascal. Yeah, but we won't even bother with that one. Okay, so 5. A glass column filled with mercury and inverted in a pool of mercury. The mercury column stabilizes at a height of 729 millimeters above the pool of mercury. What's the pressure of the atmosphere? Okay. Remember, test-taking technique. This is most of these questions, if not all, are multiple choice. So you look at the answers and that tells you what units you need to end up with, right? They're all atmospheres. So sometimes it also helps to draw a picture, right? We have a pool of mercury and we got a column in here. And it drops down to this level, right? 729 millimeters of mercury. So this becomes a unit conversion problem. So you've got this many millimeters of mercury, you want to convert it to atmospheres. So you want to end up with atmospheres. And you want, remember, this is always in the numerator. Millimeters of mercury on the bottom, atmospheres on the top. That's what you want. So what's the ratio here? You remember?
760?
Yeah, 760. So divide 760 into 729. And let's see if we can eyeball that one. It's not going to be more than an atmosphere. It's not going to be 456 atmospheres. So, well, we can do the calculation pretty quick. I thought I could estimate it. 760. All right. Anybody else want to guess? No. 959, 0.959. Okay. Actually, that makes sense. Right. Remember, that's the last thing you do when you're solving a problem. Say, does the answer make sense? Right. 730 divided by 760. That's, yeah.
30.
Yeah, it's pretty close. All right. Okay, today, if we run out of time, which I'm prone to do, then we'll have to just go do the lab. And I'll fill in the rest of it later. We don't want to cut into our lab time today. Local weather forecaster reports that the current barometric pressure is 30.4 inches. Inches of what? Inches of mercury. What's the current pressure in atmospheres? Okay, so you need another conversion factor, right? Let's see, did I put that in the back? Useful information. Millimeters of mercury and inches of mercury. Right? Inches of mercury in atmosphere. I heard that 29.92, right? Okay. So it's another unit conversion. I don't know if you remember at the very beginning, I said a huge number of chemistry problems can be solved simply by dimensional analysis. Just go for the units. Now we need a conversion factor, right? 29.92. So that should be greater than 1. Let's see, we got a candidate in there. There's one exactly 1, and the others are too big. Right? So 1.02 looks like it's reasonable. Right? Of course, that's assuming we don't cheat and look at the answer, because I got the key up there. That's just to keep me honest. How about air pressure in your inner tube of a racing bike is about 112 psi. That is high pressure. 112 psi. What else? Have you ever seen a racing bike? The tires are like that. Right? So it takes a lot of pressure to keep them inflated, I guess. And we want to convert that to atmospheres. Right? So what's the conversion factor here?
14.6.
Yes. Pounds per square inch is 1 atmosphere. So what's that? Almost 8, right? 7.62 looks like it's closest. Right. If you're trying to on these very simple conversions, when you're trying to work your way through an exam before you run out of time, sometimes you can do these in your head if you practice estimation. Right, 112 divided by, no. Like I said, practice. It takes practice, right? And if you do estimation a lot, it'll keep your mind sharp even when you're 70 years old. It'll help. Okay, now we're going to look at the gas laws, right? These are just, do you know them? Boyle's law is a relationship of what? Pressure versus volume, right? Oh, by the way, what are the four variables that will define a gas? We've got two of them there, pressure and volume. What are the other two?
Temperature.
And moles, yeah. So if you know these four factors about a gas, you can fully describe its physical behavior. And for pressure versus volume, if you're letting these vary, then you have to hold these two constant, correct? Yep. Okay, so Boyle's law would be the volume of a fixed amount of gas is inversely proportional to its pressure at constant temperature. So pressure times volume is a constant. Remember, whenever you have two variables that are product equal to a constant, that's always inverse proportion. So this is going to be constant. If that one goes up, this one has to go down. Okay. Who's next? Avogadro. He was Italian. All right. What did Avogadro say? Which one of these did Avogadro address?
The moles.
Huh?
The moles.
Moles, yeah, that's one of them. Varied according to what? Well, actually, the other one varied according to the moles. No idea? Volume. Volume and moles. So what did he say? He said volume divided by moles is a constant. So whenever you have a quotient of two variables equal to a constant, that's a direct proportion. One goes up, the other has to go up. And that would be A for this answer. And Charles. We mentioned Charles earlier. What was he interested in? These two right here. So he had to keep pressure in moles constant. And his would have looked like that. Now, those are the laws governing these, but how do we solve problems? There are two ways to solve problems in gas equations, gas problems. One is the before and after situation, right? What's the other one? We'll get to it in a minute. It's the state. What is it right now? Not what was it and where is it going? Okay. So when you do that for each one of these, right, you would have like that. And you can do the same thing for the rest of them. Just like this one. Okay, that's before and after situation. And like any equation, if you know all but one variable, you can solve for it. All right. Let's see. Looks like we got one coming up. This is 15. All right. Beware of word problems. What have I always said about word problems? They are designed to confuse. They want to test if you actually know how to pull the information out of the problem and make it work to solve the problem. So that's why the best thing to do with a word problem is start from the back and find out what the question is. And then go in and say, do I have the information to solve that problem? Is the information there? Do I need to go someplace else? And usually someplace else is periodic table. Not always, but usually. Or go to the useful information that I've given you. Okay, gaseous chlorine is held in two separate containers at identical temperature and pressure. Okay. And it's useful to draw pictures. I find it useful to draw pictures. So the temperature of this one equals the temperature of that one. And pressure is the same also? Yeah, pressure is the same. So we got the same temperature and pressure in these two containers. Container one is 1.30 liters. Okay, that volume contains 6.70 moles of gas. 6.7 moles of gas. Okay, how about the second one? Container two is 2.33 liters. How many moles of gas are in this one? That's the question. So where do we go with this? Well, this is obviously not a state function. This is a before and after. So we can use one of the laws. The relationship, pressure didn't change, temperature didn't change. So we've got moles and volume. That's Avogadro. So you got volume 1 over moles 1 equals volume 2 over moles 2, right? Okay. Now, which one of these is which? That's the trick to using these problems, because if you put these numbers in the wrong place, you're going to get the wrong answer. All right, so we identify this one as number 1. All right, this is moles 1, and this is volume 1. So these two go over here. 6.70 there, and 1.30 here. Then the volume over here is 2.33, and this is your unknown right here. Okay. So how do we solve that? Right, just a little algebra. Move that unknown over here. Move this one over there. Move this one over here. Okay, got your answer. Do I need to do it? Okay.
Velocity.
Okay. N2 then, I brought it over to the numerator on this side. And I still got 2.33 on this side. So this one comes over here. That's moles. And this one comes over here. Liters. And if we check our units, right, follow the units, right, these liters cancel, left us with moles. That's what we expect right there. Moles. All right, so to save time, I'm just going to take the answer for its, assume it's valid, 12 moles. So this should be equal to 12.0 moles. Let's see if that makes sense though. If this is 12, 12 divided by 6 is 2, and 1 and 2, yeah, that's about right. 2 and 2. Do an estimation. Oh, one thing I didn't do at the very beginning, I usually do, right? What did I forget to do? I ask you if any of these things give you problems, right? We want to attack the review document problems that gave you trouble, right? Were there any in particular that send you into fits? No? Celsius to Kelvin? Okay.
Like, I know how to convert it, but some problems you don't have to, and some you do.
Oh. Working with gases, just assume that you always convert Celsius to Kelvin. Yeah. Now there will come a time when we will use Celsius temperature in our calculations, but not when we're doing gas calculations. They always have to be in Kelvin, right? Do you remember why they have to be in Kelvin? Right, Kelvin is always positive. You have no negative numbers, right? Okay, let's see. We might have to skip a few of these if we're going to finish on time. This is worth doing. 18. body temperature is 309 K. That sound right? Yeah. What is body temperature in Celsius? Remember? Anybody here had anatomy and physiology?
Not that far in.
Oh, okay. 37 Celsius is body temperature. And put it in our formula, remember? Fifth C plus 32. Put it in there and it comes out 98.6. Okay. All right. I digress. So if body temperature is 309 K, right? And on a cold day, the air outside is 276 K. What volume of air must a person with a lung capacity of 2.2 liters breathe in to fill the lungs? So if you're going to breathe in and fill your lungs to a capacity of 2.2 liters, which temperature goes with it? This one, yeah, 2.2 liters. Right. And then this is going to be the unknown volume. Okay, so we're talking about volume temperature. That means Charles. And as long as we keep these together, we can put them on either side. Oops, we showed up. Desiree. Right. So we can say this is V1, this is V2. This will be our unknown. And we'll substitute for this one 276 K. We'll substitute for this one 2.20. And we'll substitute for this one 309. And that'll give us the volume of air that you have to drag into your lungs to fill them at your temperature.
And you do like you did the last one anyway.
Mhm.
Okay.
Yeah. This one's better because that one's already in the numerator. We just have to take this one over here times that divided by this.
So you times,
So we're having 2.20 times 276 divided by 309. Right, and that'll equal to the volume, which in this case should be 1.97 liters. Let's see if that makes sense. That's about 2. This is about 2, and these are pretty close together. You know, I'll go for that. Let's see what we got next. You're holding 2 balloons, an orange balloon and a blue balloon. Orange balloon is filled with neon and the blue balloon is filled with argon. So we got one balloon filled with neon and one filled with argon. And this is 20. Okay. The orange balloon has twice the volume of the blue balloon. Which is the orange. Orange is, excuse me, neon. And this is blue. So the volume of this one with neon in it is twice the volume of the argon. That means it's 2 times the volume of the argon. That's the way you would express it mathematically. All right. Which of the following best represents the mass ratio of neon to argon? So we're looking for mass of neon ratio to the mass of argon. So how do we approach this problem? Right. We can say things about the number of argon atoms in there, the number of neon atoms in there. Right. If this one is twice the volume of that one, then this one has twice as many moles. So the moles of neon are equal to twice argon. All right, who said that? He was Italian. I'm sorry. Avogadro. Yeah, Avogadro. Okay, so now we know if we have, excuse me, if we have twice as many neon atoms in here as argon atoms. But the volume over here is twice as big. Then the mass ratio is going, let's say neon is about 20 and argon's about 40. Okay. So if we have twice as many particles in here as we do there, what's the mass ratio?
1 to 2.
If we had, okay, if we had equal numbers of particles on both sides, then each one of these would weigh twice as much as each one of those. That would make this mass twice that. But this has twice as many particles in it. So it'd be 1 to 1.
1.
Yeah. If you've got twice as many particles over here, you just double that mass. And now they're equal in mass. So it's 1 to 1.
Oh.
Yeah. I have worked this out algebraically before, but it loses students. So we're trying to approach it logically this time. All right. And as usual, we skip a few because there's a lot of redundancy in that document. Remember, what are your two best friends in chemistry?
Non-redundant and
No, that's for naming compounds. But you're right. Right. When you name a compound,
we
that,
don't want extra stuff.
right. It forget the terminology now.
In your like useful information, is STP in here or no?
I don't know.
But
The SDP for gases,
what
Okay.
is the-
standard temperature and pressure for gases. Temperature is 0 degrees C.
Yeah.
For gases only. But all other chemical reactions, the standard temperature is 25 degrees. But the pressure is the same for any of them. Okay, 1 atmosphere. And then when we get to reactions where we're looking at standard concentrations, the standard concentration then would be 1 molar. But we haven't got there yet. That's just,
and then the R is 0.0821.
Oh. yeah, for, I believe that's the one we're going to use, the gas constant 0.08206. When the units are liter atmospheres per mole. Okay,
And that's in the useful information that ours are.
there's several of them in there, aren't there?
Yes.
Yeah. The other one that we'll use at some point in the future is this one. 8.3145. And that changes this numerator to joules, which is a unit of energy.
But not on this.
But not on this one, no. I don't think we need it on this one. Okay, let's see. A gas sample is heated from -20 to 57. Increase from 2 liters to 4.5 liters if the initial pressure is, okay. To solve this problem, and I'm racing the clock. So to solve this problem, what you need is the combined gas law. Do you remember that one? P1 V1 over N1 T1 equals P2 V2 over N2 T2. And in fact, you can derive any of the 2 variable gas laws from this one. All you need to know is which ones are held constant. In this case, we're holding the moles constant. So if we take that out and that out because they don't change, then this is the law that you would use to solve that problem. You just have to identify what's 1 numbers and what's the 2 numbers, right? And what I've advised you to do is set up a chart. And put the values in the chart first. Which ones are related to each other here, which ones are related to each other here. Then when you put it in there, they'll go in the right place. Right? If you don't, there's a chance that you can get them moved around and end up with a big red mark on that paper. Okay. A sample of oxygen has a volume of 1.72, and how many oxygen molecules does it contain? All right. This is, why don't we go ahead and work this one then? Because this one is a multi-step problem. Remember, oh, we didn't answer the question I asked. What are your two best friends? Curiosity. You always want to know more about something. And the second one is boredom. If you work all those problems that I give you as samples and you get bored working them, then you probably know them pretty well. Okay, number 30. A sample of oxygen has a volume of 1.72 liters at 27 degrees. Aha. Okay. Let's put what we know up here. 1.72 liters equals volume. And temperature equals 27 degrees C. We know we're going to have to convert it, so we just go ahead and add that to it. 300 K. What else do we know? Pressure. 800 torr. Okay. So is this a before and after or a state function? We only have one volume, one temperature, one pressure. That has to be a state. Yeah. So the formula that you're going to go for is the one that addresses the state. Right. That one right there. Remember that one? Ideal gas equation. Okay. So we got pressure, we got temperature, we got volume, pressure, temperature, volume. And the question was, how many oxygen atoms are there? Well, this is not going to tell us how many atoms, it's going to tell us how many moles. Then we can convert to atoms or molecules. Yeah, molecules. And we know that R is a constant. All right, so we can either plug the numbers in and solve, or solve it for our unknown and plug the numbers in. Oh, by the way, in this equation, whatever R happens to be, in its units of measure, okay, that dictates the units for each of the others. This has to be in liters. This has to be in atmospheres. That's moles, and that has to be K in order for this to work. Okay, so that means this has to be converted to atmospheres. Okay, whatever that happens to be. So I guess we better, yeah, somebody do it for me.
1.0. Right?
Yeah, that's good. Atmospheres. Okay, so if we solve for moles, that would be PV over RT, correct? And pressure is 1.053 atmospheres. I'm going to leave the units out because we know they're right then. 1.72 liters, 0.08206. And then temperature is 300. And that will give us the number of moles. There's only one calculator working here. What you got? Well, no, we're not finished yet. This will give you the number of moles, convert to molecules. So what'd you get for moles?
662.
Is the decimal in here somewhere?
My calculator was on a little bit of funny stuff the other day too.
Okay,
Yeah, I downloaded a scientific one from Desmo on my phone of that, because my calculator started doing crazy stuff.
Okay. 1.053, 1.72, 0.08206, and 200.
About 0.105.
And I got 7.36 times 10 of those two.
Okay, I got that.
You got it.
See, when I put it in my calculator, just how you wrote it on the board, parentheses and all, one divide sign.
Uh-huh.
It gives me this weird number, but if I go back and do that top. Divided by the 0.82,
Uh-huh.
divide again by the 300, it doesn't right, but it won't do it if I do parentheses over.
No,
Why?
I don't know. That's an algebraic calculator, isn't it?
It's scientific, I think.
Yeah,
I feel like it's on-
yeah. I don't like algebraic calculators, but they seem to be the most popular.
Yeah,
Mine's reverse Polish now logic, which means it doesn't need parentheses.
Oh.
So I'm less likely to make a mistake.
you have to put times.
No, it's set up so you say like 1, enter, 2, then whatever you times it equals. And when you say times, it spits out the number as 2. You don't even have an equal sign.
You can check me later.
It's they're not, I don't know why they're not more popular. They're fairly popular with engineers, right? But not with the general public. Okay, so now we've got this many moles. How do you convert moles to molecules? What's the conversion factor there? Moles on the bottom, right? Molecules on the top. We want to cancel moles. 6.022 times 10 to the 23rd. You ever seen that one before? Avogadro's number times that value should give us 4.43 times 10 to the 22nd. Let's see, we have the right number of, yeah, 3 significant figures, 3, okay, we're good. That ate up a lot of time, but I feel like it was necessary. Okay. You remember the conditions that are most ideal for a gas? What do we mean by ideal when we talk about gases? Okay, conditions for ideal behavior. Gas. Always. Under any conditions, it's always a gas. In other words, you squeeze it and cool it, it will not condense. Okay. And if we think about this in terms of the kinetic molecular theory, what are those gas atoms and molecules doing in there? Well, they're bouncing off each other, right? Even though they're very far apart, they're going to smack into each other. And when they do, how do they behave? They behave like billiard balls, right? They just go like that. No interaction whatsoever. That's an ideal gas. Okay, so what conditions contribute to that? Well, if you think about when the atoms bang into each other, what would overcome any interactions that they would have? One is high temperature, like lots of kinetic energy, right? Would overcome any type of interaction. And low pressure, which is synonymous with low moles. So if there are very few atoms in the container, the chances of one encountering another one are reduced. So the gas is mostly space anyway. And we guarantee it's mostly space by low pressure and low moles. So let's see, which one would do that? Low pressure, high temperature, and low moles. E would work best for ideal behavior. Now, do we have that? Right now in this room, do we have high temperature and low pressure? Guess again. Yes, we do. Compared to what? Compared to absolute zero? Right. Yeah, we've got relatively high temperature and pressure as compared to what? Well, as compared to maybe the surface of Venus, or as you go down in Jupiter's atmosphere, the pressure kind of goes. Right. So technically, and on a relative basis, we have high temperature and low pressure right now, right here.
What would high pressure feel
Uncomfortable.
like? Your body hurts. Like when they go underwater, like, I don't know what they're called. They go real deep dives and they have to come up super slow. Why is
Yeah.
that?
Oh, are you talking about scuba divers? Okay, yeah. When you go for every 33 feet you go down, that's another added atmospheric pressure. So if you go down to 100 feet, then you've got what, 3 extra atmospheres plus the one above. So you got 4 atmospheres on your body. So what does that do? Let's see, we covered solubility of gases yet? I don't remember if we have. Yeah, we have. Yeah, Henry's law. Yeah, solubility of gas goes up as the pressure goes up. So the air that you breathe is oxygen, that's what you need, but it's also 78% nitrogen. So and nitrogen will dissolve in your tissues under extreme pressure like that. And your tissues get saturated with nitrogen, only it doesn't do anything, but just sit there until you reduce the pressure on your body, and then it comes out of solution. So if you come up too fast, it comes out of solution where it shouldn't, like in your joints, in your organs, in your brain, and gives you what they call the bends. So that's why you have to come up in stages if you're down that deep. My wife used to be a scuba diver, and she tells me about going down. She says, I don't want to go any further down than 30 feet. Because at 30 feet, you can just pop right to the surface. Plus, that's where all the interesting stuff happens anyway. You go much deeper than that, then it gets too dark. Anyway, let's see how we're doing on time. Let's see. You got till what? 1:45. We got 30 minutes left. Okay. Let's see. Let's try a different one. This won't take much time. 49. Just to see if you remember what we mean by diatomic molecules. Diatomic means what? You break the word apart. What does di mean? 2. And so it's got 2 atoms, right, in the molecule? Okay. Which one has 2 atoms in the molecule? Yeah, only chlorine. Right. We have other diatomic elements, right? Which ones are those? You remember? Hydrogen. The inverted L. Like that. Nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Those are all diatomic. So if you read a word problem and it says bromine reacts with, I don't know, oxygen, you know that you have to write Br2 plus O2 yields a product. Okay, otherwise you'll never get the problem. Let's see. The mass of 1.12 liters of gas Y at STP is found to be 6.23 grams. The density of gas Y is. All right, let's do this one. What are we given and what's the question? We're looking for the density of Y. Right? So that means we have to know the mass of Y and the volume it occupies. in order to solve the problem. So what are we given? 1.12 liters. 1.12 liters. Right, there's the volume. At STP to be found 6.23 grams. Well, this was easier than I thought it would be. So, and look at the answers. They're all in grams per liter. Grams per liter. So 6.23 divided by 1. That's about 6, isn't it? Closest one there is 5.56. I think that's probably the answer, don't you? Oh, this is what I was getting at. 53. I knew there was one that was more fun than that. We're looking for the molar mass of gas Y. When we have this information, that and that. So the molar mass, which I abbreviate molecular weight, it's not correct, but it's part of my history. We need to know the mass per mole. All right, we know the mass right here. Got it. How do we get the moles? Well, we're also given some more information there that I didn't put on the board. Standard temperature and pressure. So we know the temperature is equal to 0 degrees C or 273 K. Okay. Standard temperature and pressure. Standard pressure is 1 atmosphere. Right. So can we get moles? Right, we've got the mass already. How do we get moles from a gas? It's not a before and after situation. It has to be a state function. So if we use this one, and we solve for moles, PV over N, excuse me, RT, that'll give us the number of moles, won't it? Now, if we use a little algebra, maybe we can do this all in one calculation. We don't have to do 2 calculations. Right, there's the N, there's the N. If we take this group right here and substitute it right there, what does that give us? Well, it gives us mass, and that gives us PV over RT. And remember, the denominator of the denominator is the numerator. So this one flips up here, and we have nRT over PV. Let's see, are we going to do that lab in this class? Hold on a second. Yes, we are. We're going to use this right here to do the last lab in the class, the Dumas method. Right?
What did you call
The Dumas method.
it? The Dumas?
DUMAS. The French don't pronounce S's at the end. Okay, so that's molecular weight. So now we know the mass, we know R, we know temperature, we know pressure, we know volume. We can solve molecular weight just by plugging the numbers right in there. Right. So somebody going to do that? We're working on it, right?
$124.61.
Yeah, round it off, 125. You got it. That's it. Calculator works, doesn't it?
I remember that one.
Or is it the operator?
Get me a little bit.
I often wonder. It's like that, what's that T-shirt I've seen before? Oh, I know where I saw this. It was on the water, no, not the water boy. It was an Adam Sandler movie where he was a golfer. Remember that one?
Happy Gilmore.
Happy Gilmore, yes. And one of the characters there was that big guy. You know, the big monster guy. He had a shirt on that says, "Guns don't kill people, I kill people." Okay, let's see. How about this one? 56. Right. Which one of these graphs would give the proper relationship between pressure versus molar mass? Pressure versus molar mass. Okay. Well, we can define pressure in terms of this equation, right? We can define this one in terms of molecular weight equals mass per moles. So if we combine those two equations, maybe we can come out with this one versus that one equals something. Right? And if you look at the graphs, they're going to be something like this. So which one would be the independent variable? Which one do you change? Molecular weight or pressure? I think pressure would respond to molecular weight. So this would be there and there. What would that look like? Okay, so if we solve this one for PV over RT and substitute that right in here, right? Yeah, that should work because we still have P and molecular weight in the formula. So molecular weight equals M, I think we did this one before, didn't we? PV over RT. And this becomes RT mass over V. Molecular weight. Well, what we want to do is get pressure and molecular weight on the same side and see what we got left. Molecular weight times pressure, right, equals RT mass divided by volume. R is a constant. Temperature's not, we're going to have hold these things constant. Temperature constant. The mass of the different molecules, they have to be constant. If we're going to let molecular weight vary, then all of these have to be constant. So if this is a constant, what does that look like? Variable times variable equals constant. Looks like Boyle's law, doesn't it? P times V equals constant. And what is the shape of that curve? Right, there's a name for it. Starts with an H. Hyperbola. 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 Okay. Now, in math class, right, do you remember the hyperbola from math? No? Well, I won't bore you with details. But do any of those look like that? No. None of them do. So that's why the answer is E. Let's see. I'm going to have to skip that. That's probably the empirical formula. Guess what's the molecular formula? This one might be worth 61. Okay. 0.72 grams of a liquid is vaporized at 110 degrees and 0.967 atmospheres. The gas occupies a volume of 0.559 liters. The empirical formula of the gas is CH2. What's the molecular formula? Do you remember doing empirical formulas? We had mass percent of each element. We could do the empirical formula. Then how do you go from the empirical formula to the molecular formula? Right? If that's the empirical, you need to know that multiplier. Remember that? Okay. So we need to find the molar mass of this gas to compare to the empirical mass. So let's do the empirical mass while we're here. All right, carbon is what? Grams per mole. 12.01, right? Okay. And 2 times 1.01 So it's 304, 1403 grams per mole of this formula. So if we're going to do molar mass, oh, we had that formula already. We have to do it again, right? PP equals nRT and N equals PV over RT. And then molecular weight is equal to mass per unit mole. So then we substitute this right here for that, M over PV RT. And the RT comes on top, so MRT over PV. So do we have all the information we need for molecular weight? We have mass, we have temperature, we have pressure, we have volume, and we know that constant, so we can do it. So the true molecular weight of this compound will be 0.72 grams. R is 0.08206. Temperature, 110 plus 273, right? 383. Okay. Divided by pressure in atmospheres, 0.967. Correct? And then volume, what's the volume? 559. Okay, so that'll give us the molecular weight.
$42.
42.
Okay, sorry.
0.08 grams per mole. Okay, so we find N by ratioing those two, don't we? 42.08 divided by 14.03 is approximately what? Let's see.
3.
Yeah, about 3. So if this is 3, that means C3H6. 6 would be the molecular formula. And that would be C for our answers. Good deal. I like it when I don't have to do the calculation. Oops. Am I erasing something you need? Good, okay. How much time we got left? About 14 minutes. Let's look for a good one. Let's see. And if you haven't remembered, Brightspace has this key in it also.
I'm not quite in one, so.
Oh. Have you been watching the highlighted ones as we go by and marking them?
You go with the speed of light. There's
Is that a speed of light in the vacuum or a speed of light through diamond? Because it's a little slower if it's in diamond. Okay. Let's do 80. Ooh, this one's starting to give out on me. Okay. If M is the molar mass R, the gas constant, T temperature, P pressure, which of the following expressions represents the density of gas? Okay. Density defined as what? Mass over volume, right? Okay. So what else do we have? We have the gas equation, right? PV equals nRT. Let's see. Oh, we need something with molar mass in it, and they're using a big M for molar mass. So we need that one also. Equals mass per unit mole. If that were going down to 2. Freshman. Okay, so what we're gonna try to do is combine these 3 equations so that we can get something that's equal to, let's see, density. Density is what we want. Density equals something. Okay. So mass, we can get from this one, right? So M equals molar mass times number of moles, right? So we got that part of it. Molar mass times moles in the numerator. How about volume? Well, we can do volume here equals nRT over P. We plug that in. nRT divided by P. So that means, remember, denominator of the denominator is the numerator. So we can say M N P over nRT. Notice we got N in the numerator and the denominator cancels out. So that's the molar mass times pressure divided by gas constant times T is equal to the density. Right, that looks like A. Too much algebra.
I'll bring you the 3 intake mass,
Where?
D. That's mass.
That's mass, yeah.
Okay, jump over. Right. The medium.
Oh, that's molar mass. I usually write it MW.
And in the top,
And that's mass,
the same.
the same mass as this mass. Yes. That's why I solve this one for mass and take this term and plug it in right there. Yeah. And then we just rearrange and cancel terms, and this is what we got left. Okay. All right. Let's see what else we got going for us. We got isolate metals. Oh, this will be a good one. 81. This actually gives, we do some chemistry with this one. Okay. One way to isolate metals from the ores is to react the metal oxide with carbon, shown in the following reaction. So this reaction with an unknown metal. Now this is not molar mass. This is a metal. Okay. They're changing symbols on us. That's a solid. And let's see, we're going to react it with carbon. And we get the pure metal plus carbon dioxide. Okay. Now, what else are we given? If 34.8 grams of metal oxide, 34.08 grams of metal oxide react with excess carbon, right, so it's not limiting. We're going to consume all of this, and we got plenty of carbon. And 4.37 liters of carbon dioxide are produced. 4.37 liters of carbon dioxide are produced as a consequence of this reaction at 100 degrees Celsius and 1.50 atmospheres. What's the identity of the metal? What do we need to know to identify that metal? We have 2 choices. Either the atomic number of protons, can't get that from this, but molar mass will also help us, molar mass of the metal. And then we can just look along here and usually find it. Okay. So we need the molar mass. That means equals mass per mole. We got the mass right here. We got the mass of this. We don't have the mass of that yet. And we can't find the number of moles of this because we don't know the molar mass of that. So we need another approach. But we can find the number of moles. we actually need, we need the mass of this. And we need the moles of this. That's what we need to identify it. Okay. So can we do the moles here? Yeah, all we need is the moles of this, and we can use the ratio of 1 to 2 and find the moles of that. So we're good for that one. Let's do what we know. Right? PV equals nRT, right? So we're looking for moles, which is PV over RT. So what's the pressure? 1.50 atmospheres. That's in the correct units. How about volume? That's in the correct units. And the R. And the temperature. Plus 273. So 373 here. So that's the number of moles of carbon dioxide. Got it yet?
0.214.
Yep. That's moles of CO2. So how many moles of metal do we have? We need a conversion factor, right? CO2, metal, and we get that from the coefficients. 1 here, 2 there. Well, that means 2 times that, right? 0.428 moles of the metal. Okay, we got the moles of the metal. Now we got to figure out, how do you get the mass of the metal? Well, let's see. Did I put everything up there that needed to go? Just carbon. The metal. We need to find the mass of that right there. Well, let me see. Drawing a blank. We know how many moles of that is. We can find out how many moles of this there are. I wonder if that'll help us. Well, look, we've got 2 there and 2 here. So this is the same number of moles here, 0.428 moles, right? 2 to 2, moles to moles. So the molar mass of that compound would be 34.08 grams per 0.428 moles. Right? Let's see if that gets us anywhere. I'm trying not to go to my work problems and cheat. So that's 79.63 grams per mole of that compound. Okay. Okay. How do we get the molar mass of a compound? You add the molar mass of each of the atoms, right? So how much of this is contributed from oxygen? Just 1 oxygen, right? 16. So that's no, sorry. 6 or 9 is 3. 3. 6, 63. So now we do know 63.63 is the molar mass of that metal. Copper? Copper looks like it's the closest. Okay. I was a little slow on the uptake there. We got about 4 minutes left. Standard temperature for gases, 0 degrees. That's 82. Standard pressure is 1 atmosphere. We covered that earlier. Oops. I'm moving at the speed of light again. Let's see. Affected over water, okay. We haven't got to using the law of partial pressures, Dalton's law of partial pressures. Maybe we spill over a little bit, because this lab is not that difficult. This is going to need this will work best if we draw a picture. So we're collecting a gas over water. Remember, did I do this one for you guys? We have a vat of water. And then you have a graduated cylinder inverted. So there's the base. And it's marked off in milliliters. And then you have the reaction vessel over here that's delivering, delivering the gas as a product of the reaction there. Right, this is filled with water first, and then we collect a certain amount of gas here, and we can measure the volume right there. Well, the volume is 142 milliliters of gas. 142 milliliters equals the total volume of the gas. Okay, at 22 degrees, 22 degrees C equals temperature, and 753 torr. 753 torr. All right. What's the volume of the dry gas at standard temperature and pressure? Remember, Dalton's law of partial pressure says the total pressure equals the pressure of gas A plus the pressure of gas B. In our case, gas A is what we collected, gas B is water vapor. Okay, so the total pressure is that one right here, 753 torr. What's the partial pressure of water? It gives it right to you right there at 22 degrees, it's 20 torr. So we solve for this pressure, which is the pressure of A equals 753 minus 20 is 733 torr. Does that answer the question? Wait a minute. What's the volume of the dry gas at standard temperature? Well, there are two ways to solve this problem. One is, now that we know the pressure and we know the temperature and we know the that's the total volume. We know the pressure, the temperature. We don't know the moles. All right, so we're gonna have to use ratio. What part of 750 torr is 20 torr? We use a ratio. Excuse me, that's not right. We want to know the volume of the dry gas. So the dry gas is 733 torr relative to 753 torr total. And the volume of the total is down here at 142 milliliters. And this is our unknown. It's a ratio. Remember, the pressure is proportional to the mole fraction, and the mole fraction is proportional to the volume. So now if we solve for X, let's see, I'll do that one for you. 733 times 142 divided by 753 is 138 milliliters. All right, so none of these. Right. Closest one is 136. Okay, so if you had 5 real answers and none of the squirrely ones, like none of these or 2 of the above and that kind of stuff, then you would pick 136. assuming E was something wild. But 138 should be the volume and it's not there. Okay, that's another similar one. 88 is similar to that, using Dalton's partial pressures. Oh, this is a good one. Shoot, I'm already over. Let's say if we can get done by 2 o'clock, then we should have enough time to do the experiment. We got enough for 2 groups now, don't we? Unless somebody else shows up. All right,
We
2.
lose that.
Huh?
Have we lost that?
No, they're just not showing up. All right. Yeah. Meredith usually sits back in the back. Oh, Trinity is on. So Meredith's the only one we're absolutely missing, and Desiree is Zooming, so I'm not sure if she's going to be here for the lab.
I'm going to be there. I'm getting ready to pull in.
Okay, she was listening. Right. So let's see if we can solve this problem. We have 2 bulbs. Let's see, number 94. 94. Yeah. That one. Just pull out another one. We have 2 bulbs. One is 3 liters. Connected with a valve to 2 liters. Right, 2 liters and 3 liters. All right. The 2 liter has a gas in it with a pressure of 1.80 atmospheres. And the 3 liter has a 3 atmosphere pressure. Okay. Oops. All right, that's all we're given. What we want to know is what's the final pressure once the valve is opened. Which way is the gas going to move? It go this way, yeah, because that's 3 atmospheres and this is 1.8. Right. So this is going to move that way. And qualitatively or semi-quantitatively, what should the pressure be? It should be between 1.8 and 3, right? When this one moves, it's going to drop, and when it goes over here, it's going to increase this one. So it'll be between 1.8 and 3. Right? So how do we do that? Well, we have to use a little trick. We're headed for Dalton's law of partial pressure. So the pressure of the 3 liter plus the pressure of the 2 liter will be the total pressure. So what we're going to do is use a device that was put to good use by Albert Einstein himself. It's called a thought problem. A thought problem. Thought problem.
Okay.
Yeah. He just sometimes we call it daydreaming, but he daydreamed in calculus. Anyway, what we're going to do is say, what if that bulb were evacuated? It's a vacuum. So when we open this, all of that flows into here and equalizes. You can determine what's the pressure due to this gas, if that's a vacuum. And then we're going to turn around and do the same thing, make this a vacuum and let that one move. And produce the pressure that it would give in the new volume. So the pressure due to that one through a vacuum and the pressure due to this one through a vacuum, then add them together. And that'll be the total pressure. Right. So if we've got pressure and volume, this is a before and after problem. Right? P1, V1 equals P2, V2. Right? If we're going to let that one be a vacuum, then we'll calculate this one first. Right? P1 is 1.8 atmospheres and V1 is 3 liters. Okay. P2 is the unknown. Right? That's the pressure that we're looking for. What's the volume? Plus 2. because it's moving into more volume. It's going from 3 to 5. So this volume is going to be 5. So we say 1.8 times 3 divided by 5 will be the new pressure.
How many? Oh, we got the 5 because you added the 2.
3 plus 2, yeah. And that's going to be the same thing for the next one also. The final volume is increased
0.8.
times 3 divided by 5. I get 1.08. Is that what you said? Okay. That's if we let that vacuum and we move this gas over there. Now, if we come over here and we say, now P1V1 is relative to this one. So pressure 1 is 3. And volume 1 is 2. And the new pressure will be this one times 5. So P2 is now going to be 3 times 2 divided by 5. So that's 6 divided by 5. Which is 1.2. Yes, now we just plug them up here. Right? We got the 2 independent. If I did that right, 1.20. So that's 2.28 atmospheres. Well, it's between 1.8 and 3. Right? We got that much going for us. Let's see what our selections are. Okay. I said 2.28, and this answer says 2.52. Okay, did I make a mistake in calculations? 1.8 times 3.
I think you have the 3 and the 1.8 in the wrong place.
Oh. 1.8 atmospheres for 2 liters. Correct?
Mhm.
Should be over here. And this one is 3. Okay, so this one needs to be 3. So that's 9 divided by 5. Is 1.8. 8. And this one would be 1.8 here times 2 is 3.6 divided by 5 is 0.72. So now let's do that again. 1.80 plus 0.72. 2.52. Yeah, okay. Now it agrees with P. How easy it is to mess up. Okay. Give Desiree time to get here. Let's see, 95, 96. Let me look down here and see if there's anything. I don't want to miss anything really important. All right, root mean square velocity. All right, these ones that I just skipped, Dalton's law of partial pressures, you can define that yourself. Partial pressure of each one of these gases in a sample of gas were found to be these values. Calculate the mole fraction of nitrogen. Remember, the mole fraction is proportional to the fractional pressure. So if you want the mole fraction of nitrogen, you want the pressure of nitrogen, and then you want the total pressure. So the pressure of nitrogen plus what was the other pressure of methane and the pressure of oxygen, and that'll give you the mole fraction of nitrogen. Okay, this is 95. And Dalton's law, you can get that one. Let's see about calculate the root mean square velocity. You need the formula, which is in useful information. So just go to the document, look in the back. You have to know what you're looking for though. Because I don't build a roadmap into this thing. Right? 3RT over M. So M is molecular weight. And this is the root mean square velocity. Yeah, root mean square velocity. So let's see, do we have the information here? Oh, by the way, we are going to use the R value 8.3145. 8.3145 times the temperature. What was the temperature? 11.8 degrees C, which would be plus 273. Has to be K, because this is joules per mole K. There she is. Those are extras unless you need a copy. And the molecular weight, molar mass of oxygen gas. So how do you know that one? Yeah, 2 times 16. Except, this is crazy. 32 grams per mole. But this R requires SI units for mass. So what's the fundamental unit for mass in SI? Kilogram. So you got to convert that to kilograms. 32.00 times 10 to the minus 3 kilograms. Remember, when the unit gets bigger, grams to kilograms, the number has to get smaller. Right? It's 1,000 times difference. Or if you want to, you can use conversion factor, like grams on the bottom, kilograms on the top, right? 1,000 grams per kilogram. And that gives you 10 to the third in the denominator, 10 to the minus third in the numerator. So it'd be 3.200 times 10 to the minus, excuse me, 10 to the minus 2. Right? Because we took an order of 10 and put it over here. Now we can put this in here, 3.200 times 10 to the minus 2. And that'll give us the root mean square velocity in what units? SI units. Meters per second. Whatever that comes out to be. Should be 471.2 meters per second. Okay. Well, I'm out of time. So the ones that we missed, there's Graham's law. That's just a memorization. Okay. Oh, you're marking them down? Okay. 116, 117, 118. Okay. 124. And 132. These are just sample problems, but they are worked out in that handwritten work problems. Okay.
We're getting back to this. Start with 103.
103.
Oh, we missed it.
Okay, there's 103. '96, '95, '94. 88. 86. 83, 82, 81, 80.
Now, all of these are on that worked out
Yes.
too, so we can rates for reference
Yes.
that to figure out how to work them out.
Yeah, they're right here.
Okay.
In fact, the order that I suggest is you take the review document, try to work all those problems yourself. And make note of the ones that you have difficulty with, focus on those, and if you can't figure that out, then go to the handwritten worked problems. Right? And if it still doesn't make sense, then bring those to class.
Okay.
Oh, okay. Keep rolling.
Yeah, she's not allowed to do that.
61. Got it? 58. 56, 55. 53, 52. 49. Okay. 40. 37. 30, 29. Probably got most of these then. I don't think I skipped any this time. 20, 18. 15. 11, 10, 9, 8. 6, 5, 3, 2, 1. Okay.